Too nice. All right, so anybody have questions from any homework? All right. I'm an optimistic fool. I'm going to take that to be a good sign. Let's see. I still do need to update the update of the update for the homework. So I'll do that eventually. We left off, we did some polar graphing. And all right, so what I'm going to do, let me come back to this section here. Yeah, here we go. So you've got that one handout. Let me remind you about this. And the homework is kind of nice in the sense that they, oops, crap. They, what do you call it? They group the homework by shape in a way. You'll see what I mean when you get to this homework. But something that will be very helpful is this sheet here. Not the first part, but the second part. Here we go, right? This, this will help you as you go through the homework a bit, and not just the stuff that's in here, but the stuff that's out here also. So the roses and stuff. So we might try to do a rose. I think tonight I'm going to actually show you the, well, we'll see. I don't know. It depends. We might get to the butterfly graph tonight if we can get far enough along. So this is not a bad sheet to have sitting next to you while you're doing the graphing section. Let me see. I've got a chat. Golden rectangle. Where did that show up? Did that show up in summer? That's related to Fibonacci sequence, I guess. Is that? Did that show up in the book somewhere? Did I miss that? Golden rectangle? No, you're not going to give me any more than that? Okay. Let me see. I'm very curious now. Oh, here we go. Oh, okay. So you're just asking generally, like you've heard of a golden rectangle? Did you know it was related to Fibonacci sequence? Oh, okay. What do you, okay. I got you. When did it come up? Everybody else thinks I'm talking to myself, by the way. I love it. There's private chats coming at me. I'm just curious because I don't really hear about. Okay. Yeah, so when we get to sequences, I pretty much always, if I ever talk about sequences, I always sneak in something else, Fibonacci sequence, because it's insane. It's everywhere. It's crazy. It's in music, it's in art, it's in the way that our body is put together, it's in the Egyptian pyramids, it's in whatever is aesthetically pleasing to our eyes, to our ears. It's insane. It's in finances, this Fibonacci sequence. Anyway, so yeah, that'll come up later. Okay, so this section here, no matter where you are in the homework, you should always kind of try a few problems out from the most recent stuff we've lectured on. Because otherwise it's going to be too far between when I talked about it and when you try it. And then it'll be like, what the hell's going on? And then these are pretty good. You know, you can go through that, you can see them work out a problem all the way out. So it's always nice to kind of follow an example along. So don't forget you've got examples too. And just to show you the homework, if you haven't looked at this homework yet, they really hit certain things hard. Do you see repeating kind of, especially here? Holy shit, they really hit this shape hard. And then they do some funky stuff here. But it's kind of grouped by shape. So they're trying to get you, I don't think I assigned too many of these, hopefully not, but you know, it gets a little repetitive. They're trying to show you what the changing coefficients do. right, to the resulting graph. And we talked a little bit about it yesterday. I had those slider dudes. Remember, sometimes they had a little baby circle inside, and sometimes it would blow up the butt. That was a very strange way to phrase that, Jeff. Oh, it's too bad. So any questions before I jump back into where we left off? Because I'm going to leave this section behind. If there's no questions. All right, maybe we should do one example. I don't know. Do you guys want to do one example of this? You got to get in there and try them out. I mean, that's the problem. You really got to get in there and try them out. Okay, so do me this favor, everybody. If you don't have this sitting next to you, I'm not exactly sure why you wouldn't. Go right now. Get your hands on blank polar graph. Who's talking to me? In 10.1, do we? Okay, wait a minute. All right. All right. So while I'm about to answer a question in the private chat, go print out a copy of this. You should have some of these printed out for yourself already, just sitting there waiting. Somebody's asking me about 10.1. Let me see. So so the beginning of the homework. Yeah, these problems. I mean, it's not a bad idea to draw the triangle. You could try to make the dimensions kind of match your drawings. Do you have to? You actually don't have to, but I always draw a picture for myself just for a visual anchor. Is this the part you're talking about? Yeah, do you have to? No. Does it really, really help you to? Yes. And try to make, if you're going to draw these triangles for these situations, you want to try to make, the angle kind of match up with what it's supposed to be, right? Just so you have a better visual. I like it. Can somebody tell me which one of these problems only gives you angles? 6, 7, 8, 9, 10. Which one of those only gives you angles?
Number 8.
Yes, I like it because the freaky stuff is angles, right? Otherwise known as Greek letters, but we can call them freaky stuff. The other ones have 2 angles and then a side. And of course, another thing that gave it away is the degree symbol, but oh well, right? That's in there too. That'll help you out. Okay, so I have a sneaking suspicion that not a lot of you have made it into chapter 10 yet. And you can say, well, Jeff, you're the asshole that gave us all this work to do. And then I'll just remind you, you can choose to do as much of that as you want to. I'm not going to ease up on you. I'm going to tell you, finish it, correct it with the shit. But you're going to be like, I want to keep up, Jeff. So just deal with your own stuff. All right. I've had that discussion with you a few times. You've got to try problems out as soon after I lecture them as you can. The further that they are apart, the less sense they're going to make. And at least you got my videos up there to look at if you want to. So no questions on this section at all. I mean, this is the possibility of that. Remember that there were 2 possible triangles you can get depending, and you had to check both. Okay. All right. So it's, and if you have questions from chapter 9 still, you can ask those too. I don't know if people are afraid to ask me questions from 9.5 just because I'm talking about 10. Okay. All right. So let's go back here. So let's pick out a problem. I don't think I'm missing anybody. No, good. Let's pick out a problem to try. Does anyone see something here that looks like something you'd want to try? Well, let's see. That's just testing it. Shit, that scared the crap out of me. I forgot I had my heater on. Damn. I watched too many horror movies. All right, so in this section, this is where you actually have to graph stuff. Is there anything here that looks like something you want to try before I just pick one to do? Does anything jump out at you as something interesting you want to look at?
Can we do one of those R squared?
Yeah, somebody's agreeing with you. So let's look at 32. Somebody said 32. Okay. So write that equation down, and then I'm going to switch over to my polar graph paper. Let me pull it up here real quick. Oh, when I say real quick, I don't mean real quick. Let's see, where are you? Thank you, Heater, for that brief spout. Let's see. Here we go. Perfect. All right, has everybody got that equation? R squared equals 36 cosine 2 theta. Okay, here we go. I'm going to stop sharing. Pop. So this one's interesting because, well, you guys picked it out for a very good reason. It's got that R squared piece that you're like, what the hell is this going to do? All right, let me see. Let me do this. Copy it down. You guys just chill. Let's see. So R squared equals 36 cosine of 2 theta. I like it. Where'd you guys go? There you are. Okay, so. All right, wait a minute. I got the wrong thing. Dang it. Let's try this again. There it is. Okay. So how am I going to handle the R squared? What can I do to handle that? Give me an idea of what to do about this.
The square root.
Holy shit, yes. But when I take the square root, what am I going to have to put down there? Plus or minus. Yeah. Is it my speaker? I can barely hear. R equals plus or minus. Square root of 36 is 6. And the square root of cosine 2 theta is the square root of cosine 2 theta. All right. So what's going to happen is I'm going to have the 2 different R's for every input, or, almost every input, right? So when I go to make my table, and I'm going to pick my usual suspect. Now, the thing is, look what I'm doing. I'm doubling my angle. So I can actually be a lot more precise here. I'm not sure if I'm going to have room for this, but let's see if you guys follow what I'm saying. So I could put pi over 12 in. You guys with me? Because the first thing I do to it is double it. So then it becomes pi over 6, which is something I know. So see, can we do this without writing a lot of shit down? What's the cosine of pi over 6?
1/2.
No.
No, I'm dumb. Sorry. Square root of 3 over 2.
You're not dumb. Stop it. Square root of 3 over 2. So maybe we do have to write a little bit. So this will be plus or minus 6 square root of the square root of 3 over 2, right? And now we can just throw in the old calculator. That's fine. There's no real good way to get that by hand, right? So let's see, what do we get? This is a little bit funky.
I got 5.58.
Yes, cool. I like it. We'll make it 5.6.
Okay.
Right. So when you're doing this stuff by hand, it's fine to round to 1 decimal place. I mean, I can barely do 1 decimal place. Holy shit. Right?
Mm-hmm.
I mean, so on one level, it really is just brute force. But on the other level, something I haven't even done is look for symmetries. Right, so let's keep going. Let's see if we get interested in what kind of symmetries this guy has. Pi over 6. So if I throw that in, that'll be plus or minus 6 square root of cosine of pi over 3, right? If I throw this in there, it's going to be double it. Please let me know if you're not with me. So pi over 6 is kind of like my next dude up. Throw them in there, I get pi over 3. Cosine of pi over 3 is
1/2.
1/2, kick ass. So then it'll just be, oh, I forgot. I should put this down. I forgot this right here for the R, plus or minus, right? So every time I do one, I'm actually getting 2 points for the price of 1.
Sweet.
So, sorry?
Nothing. Talking to myself. Ignore me.
Okay. And then if I do this, I get 4.2. All right. And then if I put, is everybody, I mean, so there are levels of this. The more you understand, the less you have to do. So you can do symmetries, you can do so forth to help you know how much of a table do I need? How far do I have to go? But then you can just start, you just start plugging shit in, right? So if I put a pi over 4 in, that becomes cosine of twice pi over 4 is pi over 2. So what's cosine of pi over 2?
0.
0, kick ass. I like it. And then if I put pi over 3 in there, it becomes cosine of 2 pi over 3. And now this is where things get interesting. What's the cosine of 2 pi over 3?
Negative.
Negative.
1/2.
Yeah, it's negative. So anywhere that this is negative can't be a part of this, because I don't know, do you want to even imagine what it would be like if we included the possibility of imaginary numbers with polar coordinates? Do you want? No, you don't want to do that. So now that kind of throws off a bunch of possible values, right? Anywhere where the cosine is going to come out negative can't be a part of this graph. Are you guys with me? So that throws that out. In fact, let's think about what that means. When is cosine negative? Let's think about the quadrants. What quadrants? I'm sorry, go ahead.
I said quadrant 2 and 3.
2 and 3. So from pi over 2 up to 3 pi over 2, right? You guys with me? No?
But
Yes.
it could be 3 pi over 2, right? Because that's just 0. So it would be included, or would it not be included?
No, so this is where I can't use. So, right, the way I'm writing this is what I can't use. And I've made one little mistake. Let me undo it. Because I don't have theta in there. I have, oh, that's fine, Jeff. Get out of there. You're using this one. I have 2 theta in there. So let me make sure everybody understands the point she was just making. What I'm writing down here is what it's not allowed to be. So this is not in the domain. Not good. You guys with me? Please let me know if you're not with me. So this problem is, I understand why you picked it. At the same time, I want to make sure you know how to do easier problems than this, right? This problem has a little bit extra because of the fact that r squared, that means it can only be positive because we're not doing complex stuff. which means this side can only be positive, which means there's certain angles I cannot use. Anything that makes the cosine negative. Now, real quick, if twice theta has to be between these two things, then I just cut everything in half to figure out what theta can be between. I mean, not between. So these are the things I cannot use. Are you guys still out there? I cannot use these values. And notice, now here's, I think it was Amber who made this point. Can I use pi over 4? Did we use pi over 4? Yeah, we can use it just fine. And that's why that's not equal to. So these are the things I cannot use.
Why can't we use 3 pi over 4?
Because then twice that would be 3 pi over, no. Let me be careful. We can use 3 pi over 4 all day long. We can use 3 pi over 4 all the damn time. So what I'm writing down here is all angles we cannot use. It was just quicker to do that. And let me ask you this real quick. What's the period of this thing? What's the period of this function? I got so much writing up there, it's driving me crazy. There we go. Anybody? What's the period of this? Oh crap, now I can't even write. Anybody?
Is it 2 pi?
No, it's what it normally
Pi?
is. And then I put a 2 in there. So it's pi. 2 pi divided by 2, remember? 2 pi divided by the multiplier. So I really just have to go up to pi here. So I really want this. Are you guys understanding? You should have been prepared for this. And this is why you picked it. So this is a smart pick. 2 people picked this one because of the squared on the r and because of the twice the angle in the cosine. That's 2 excellent reasons to pick this problem. So this problem is going to be harder than your everyday problem you'll get otherwise. So you do have to consider things like this. What can I not use? What's not in my domain? Because then I'm not going to plug them in because I can't use them. Okay, so which means I can go straight from pi over 4 to 3 pi over 4. Let me just erase this guy. There we go. All right. It's really creepy sound effects. Oh, well, to it. 3 pi over 4. So what happens when I put a 3 pi over 4 in there? It becomes cosine of 3 pi over 2. Is everybody with me? Please tell me if you are not with me. It is okay if you're not with me. It's not okay if you don't tell me. And of course, what is the cosine of 3 pi over 2?
0.
0. I love it. All right. And then I can just keep going. Now I can put 5 pi over 6. Do you see how we're almost done? Because we're almost to the period of pi. 5 pi over 6 would be the cosine of 5 pi over 3 after I double it. Right? What's the cosine of 5 pi over 3? This is going to be the same thing as the cosine of pi over 3. Are you guys with me now? See, this section is where if you don't have your basic trig angles remembered, it's going to kick your ass, right? Or you just plug it all in the calculator, I guess. Whatever. It'll work. But come on. What is the cosine of 60 degrees?
1/2.
Yes, so I'm going to get the same as I got up here. right? Which was the plus or minus 4.2. So it's going to build back up, it looks like. So I can almost bet that if I plug in 11 pi over 12, I'm going to get cosine of 11 pi over 6 after I double it, which again is going to be the same thing as pi over 6, which will match up with this answer. I don't know if you guys are with me. I'm trying to show you some shortcuts. This happens so much because these are periodic functions. Of course, I'm going to get equivalent outputs for a lot of different things because it goes through the same values over and over and over and over and over. All right. So now we just got to plot these things. So nothing gets bigger. Oh, why didn't I put, I'm sorry. We should obviously put 0 in this bad boy, right? Let's put 0 in this thing, and let's put pi in this thing. I don't know why I didn't do the extremes. What's the cosine of 0? So if we put a 0 in, sorry?
1.
1. So the square root of 1 is 1 times 6 gives me 6, plus or minus. And then if I put a pi in there, what's the cosine of 2 pi if I put a pi in here? Cosine of 2 pi is also
0.
no
1.
1. Cosine is only 0 at the half pi's, right? Because that's when it's on the y-axis. Cosine is of 2 pi is back here. So it's going to be plus or minus 6 again. Crazy shit. All right, so let's try to plot these points. I'll do the first couple, and then I want you to finish it up. So let's kind of start down here. This is my fault for not putting 0 first. I don't know why I did that. So it goes, I face 0, and I go out 6, and I go out. So let's see. Do I go 6? 1, 2, 3, 4, 5, 6. Yay. I go out 6, and I go out negative 6. Then I go to pi over 12. So I face pi over 12, and I go out 5.6, and I go out negative 5.6. All right. Keep going. I'll sit here. I'll sit here and wonder what's going on, what's going on. I'll tell you what's going on. Mm-hmm. Can't you feel tonight? Don't ask me. It's been a variety of music today from me. I don't know. 2, 3, 4.2. So I'll go out. So I face pi over 6, and I go out 1, 2, 3, 4.2. I always forget you can't see when I do that. Let me use my mouse. And then I face pi over 6, and I go back 1, 2, 3, 4.2. Yeah, it's roughly right. Okay. So far, this looks really silly. But oh well, let's just keep going. Yeah, let's see. Okay, I'm with you. You're fine, Jeff. Pi over 4. I face pi over 4, and I go 0. All right, now stay with me now. So what have I got so far? It looks like it goes like this. I should have done a better job. Let me try to do a better job. It's pathetic, Jeff. Oh, crappity doodah. Jeff. What do you want from me? This is a weird thing. All right. I gotta do this. I can't go past pi over 4. At pi over 4, it's supposed to be at 0. There we go. Do you see what I'm trying to do? I can't go past the pi over 4 line because it's supposed to be at 0 right when it gets to pi over 4. And then the next thing is at 3 pi over 4, I go 0. Well, that's nice. That matches right up. 3 pi over 4, it goes to 0. And then at 5 pi over 6, oh, I always forget you can't see me when I do that. So I face 5 pi over 6, and I go 4.2 out. So I go 1, 2, 3, 4.2. And I find the 6 over here, so I go in the right place. 1, 2, 3, 4.2. Oh, crappity, dude. I lost it. There it is. All right. So I already see what it looks like it's going to do, right? It's going to repeat this. And then, of course, the next step out, it goes to 5.6. So I don't have to do too much there, right? It goes to 5.6 next. So 5.6. And it also goes back 5.6 there. So it looks like it's going to do this neat thing. I don't know if I didn't pay enough attention there to make sure I didn't do the. All right, so see, this is going to kind of follow that and go there. It's going to come out at the pi over 4. All right, that's good enough for by hand. So that one, I don't know. What's your feelings about that? I mean, is that something you expected to happen? What do you think? Okay, good. I haven't frozen. What do you think would have happened differently if I would have put a 3 here? A 3 here in the equation instead of a 2? Anybody? This is your time to just say some crazy shit because I'm not going to take anything off. Oh, here we go. Here comes some crazy chats. Let's see what the chat's happening. Oh, okay. Somebody asked me to go over the domain. I'm sorry, I missed that from earlier. Would it have been wider? No.
Would it have been like stretched along that polar axis?
No. So everybody with me that I'm going to put a 3 here.
Mm-hmm.
So remind me this. If it was just 3 cosine theta, that would have just been circle here, right? Remember that? One circle, one thing, one loop. I put a 2 there. How many loops do I have now?
2.
I got 2 loops. So if I put a 3 there, it's really not a bad guess. If I put a 3 here instead, I might get 3 loops, which is exactly what happens. Kind of related to that rose leaf thing. Remember the rose, the leaves on the rose is related to the number that's inside? I don't know if you guys remember. Bam. Yeah. So if I put a 4 in there, I'm going to 4. If I put a 3 in there, I actually get not 3, but I actually get 6. It's kind of like the rose leaves, the same idea. So what's really happening is you're getting this, and if you kept going, it would kind of repeat itself again. Oh, I'm tracing it. You can't see me do that. It would kind of repeat itself again. But if you put a 3 in here, it would make 3 leaves, and then it would make 3 more. So it's the odd multiples that allow for more leaves. Somebody's shouting at me. Everything triples. No. So if I put 5 in there instead of 2, there would have been 10 leaves. 10 loops. You know what I mean? 10 loops. So we can try that out here in a minute. We can just throw it into the calculator and take a look and see if that's what happens.
I'm confused because on that paper sheet you uploaded, I was reading like the rows thing, and it
Yes.
says if it has n leaves, it has n leaves if n is odd, but it has two n leaves if n is even. And now you're saying if it's
No.
odd,
So this isn't the same as that, right? This equation is not the same. You with me?
yeah.
This is a different equation than the one for the rows. Are you with me?
Yeah.
Yeah. Okay. So this one's going to act a little differently than that. It's got the reason it's got these loops is different than why that's got the leaves, but it's
Oh, okay.
this is not one of the shapes that you have to kind of know anyway.
Okay.
Yeah, this is its own deal. With the square root and the plus or minus stuff, this guy is going to act his own way. All right. So when I asked you, what did you think would happen when I put a 3 there? I didn't think you would know why or the right answer or why it's the right answer. I just wanted to see what you thought. And I don't blame you for thinking maybe it got wider or something because we're used to those doing that. But with polar graphs, it changes how often it could loop because it changes the domain. It changes how long it takes it to go through its cycle. That's why with these different kind of things, it gives me more loops the higher that number goes. And they have their own rules, right? Okay, maybe. So is this something you have to memorize for all these different shapes? No. You've got the symmetry you can check out, and then you make your tables, and you're good to go, right? Okay. All right, so let's do this. Let's check this out. Let me share my, well, let's see, what do I have in my calculator? That's right, I got, where are you, calculator? Dadgummit. Let's throw this in the old calculator to see what we get. All right, open, there we go. What are you talking about? Hold on. All right, let's try this again. There we go. Oh shit. I don't want you to see the magic behind there, right? All right. So let's go to polar. I think I got nothing here. Good. Let's put this function in here. So I'm going to have to do it like this. I'm going to have to put positive 6 square root of cosine 2 theta. And then I'm going to put, well, let's see. Let me show you this. Why do I still have it? Oh, it doesn't matter, Jeff. Ah, screw it. I'm just going to negative 6 square root of cosine 2 theta. Is that cool, guys? Because I have two different functions there, right? When I took a square root, I got plus or minus. So let me see. Let me zoom normal, zoom standard. Oh, poor little dude. Am I in a weird window? This thing, all right, let me stop. Let me make sure everybody's playing along with me is with me. All right, so there they are. When I went to graph it, I noticed, see how it doesn't really connect? Let me try to save this poor little guy. I really want you to understand this. The step size is my resolution. It's actually the number of points the calculator calculates to make the graph. So the smaller that is, the smaller step there is between its inputs. So let me make this 0.04 and see if that makes this better. All right, that's better, but it still has issues in the middle. Let me try to really crank this thing up. Make this 0.01. See if I can. This probably is a zoom issue too. All right, that's about as good as I'm going to get it. All right. And I want you to notice something else. Oh, and here's the problem. I've got my window set to 2 pi. Let me change this to be the period, right? Is everybody, again, you gotta let me know when you're not with me. Are you following along? We can change the maximum input that I use, right? So I want to go from 0 to pi. I can change that in the window. I can still change my X min, X max. I'm like Rudy Giuliani, right? From up top to down below. X min, X max, and my Y min, Y max. I can still control those. And I can also control what my theta goes from to. So if I know the period is pi, I can just put it there. So now when I do this, this will be a little more colorful. There we go. Because if I let it continue going, it's just going to like overwrite itself. So it's, you know, there you go. Are you guys doing okay out there? So let's do this. Let's try to change these to a 3. And see what happens. Oh, I didn't go far enough. Let me make this 2 pi just to be sure. Look at that. So there's 1, 2, 3, 1, 2, 3, and it ends up being 6 because of the plus or minus, right? The red is from the negative, and the blue is from the positive. So the reason it's got 6 leaves is because it was the plus or minus, giving like a reflection leaf. Do you guys see that? The blue and the red are reflections of each other. All right, and just one more. Let's put let's put 4 in there and see what happens. I probably need to change my, yeah, it's going to override it. There's the 4 leaves. All right, so if I put 5 in there, there would be 10 leaves and so forth. 10 loops. Okay. You guys okay out there? So, I mean, now watch this. Now watch this. Let me just throw this at you. Here's something you're not going to have to do. Let me think. What's a good one? I don't know. All right, I'm going off of memory here. Let's see if this does what I want it to do. I probably put those in the wrong order, but look at that weird ass thing, right? Isn't that weird ass thing? 6 divided by 1 plus 3 cosine theta. All right, obviously I didn't do that right. Oh, I know what I did. All right, now I remember. These are backwards. Gosh, it's been too long. I think so. Let's find out. All right, this is better. All right, I can tell already. Bam, look at that. Isn't that nice? What shape is that?
An ellipse.
An ellipse, look at that shit. That's right. Now watch. Let's start getting a little freaky here. What if I put a 2 in there? All right, right? That's not bad, right? So what if I put a 2 out there? All right, we get a peanut. That's interesting. What if I put a 5 in there? Okay, I'm only going to do this a couple more times, but I'm really, now look at this. What do you think what's that? Yes, it's a starfish. Isn't that kick-ass cool? I mean, that came out of nowhere. But again, this came to mind because it really illustrates nicely with a kind of funky function that when you change this number, you change the domain. We know this, which allows for more room for it to go through whole cycles, which basically allows for more loops. What happens when you put an 8 in there? I don't know. Well, look at that shit. Dude. Right? How many leaves or how many, arms on my starfish? There's 8. Anyway, sorry. I really hope that some of you guys out there hit that polar function, polar mode, and just put shit in there, right? What if this was sine? Probably the same function, just rotated, right? Yep, just rotated, right? That looks like a starfish somebody ran over. I'm sorry. That's too bad. Poor little thing. What if I do, all right, last one, I'm sorry. I get so much. What if I put weird, like 7.8? See how it doesn't match up? Which kind of makes sense. So I'd have to let it go. If I let it go further, Let me let it go 8 pi. Boom, bam, 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 bam. See how it's off, out of phase with itself? I'm sorry, somebody's chatting at me. Somebody's probably gonna be like, just stop doing this. All right, which graph are we talking about? All right, so if you're talking about this is a completely different function I'm looking at. Yeah, it was a completely different function, right? So the one we did had, let me see, let me come back here. Oh shit, where am I? So the one we did was like 6 square root of cosine 2 theta, right? And then there was a negative part, but let's just focus on one piece of it. So if I let it go far enough by itself, it makes the whole picture. Oh. Again, it's got to do with, all right, so when you have, let me come back to this. Let's do, where are they? Here we go. Hold on. Let me go back to this and just show you. Shit in half. All right, where'd you guys go? Okay. All right, so here's what that's coming from. So the roses, right? The roses. So these are kind of like, so here's the lemniscates we just did right here. And see how specifically if there's a 2 in there, it's going to be this type of lemniscate, right? Okay, you guys, so that's basically what we just did. They just had a 36 in front. Are you with me? That's going to be a very different family of shapes than a rose, because it doesn't have a square on the R for one thing. So it's not going to act the same way. So what we noticed with the lemniscate was, let's come back to this. Is that okay so far? So roses act in very specific ways. This doesn't even talk about like putting different numbers for 2. Are you with me? It was just an exploration. That's all that was. It was just an exploration about, let's see what happens, right? If we do one of these by hand, you would see why this is true. It starts to retrace itself. It's how can I say this? Yeah, let's try this real quick in the calculator. Shit. All right, there we go. All right, nope, that's the wrong thing, Jeff. Try again. There it is. All right, so let's see. If we do a rose, let's just do 5 sine. I'm sorry. Yeah, we could do cosine of 2 theta. All right. Actually, let's do 6. So that's sort of like what we just did. Just no square root, right? All right. So with roses, it's going to have double if it's even. With lemniscates, it seems to be the other way around, right? And it has to do with how much room there is within the domain for it to kind of like retrace itself. So to be honest, now watch, if I put a 3 in here, let's see what happens. All right, now I really want you guys, do you notice what's happening? I'm going way too far here. Let me back up here for a second. It's still going, Jesus. Let me make this back to just 2 pi. Holy crap. All right, let me graph this again. I don't know if can you guys see how it keeps going after it's done? Do you understand what I'm saying? So let me change this a little bit so I can make it do that again. All right, now it's done, but see how it keeps going? It's just retracing itself. Now let me take it back to 2. It stopped. So what's happening is, because of the room it's got to operate in, if I cut the domain in even parts, the halves, fourths, whatever, it's gonna actually have enough room to, and it's not gonna overlap with what it's already drawn. Is that helping at all? You can actually see it happen on the calculator. So again, if I change this back to any odd number, it's still going. It's still going right now. I'm pretty sure you guys can see that. Let's see. I got a chat coming at me. Okay. Trust me, I understand. This is all very new, and it's not something we have a good feel for. So XY coordinates, you guys have a good feel for. It's going to be parabolic. It's going to be whatever. You got a great feel for shit, because you've been working with that for a while. How long you been working with polar coordinates? Most of you not long at all. So you got no feel for anything. I don't blame you. Okay. Let's see. What else was there I wanted to do with this? I can't remember now. Ooh. It only happens. Oh, I see. When you say it only happens, you mean what? So right now, exactly, the graph overlapping. So if I put 6 in there, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But if I put 7 in there, see how it came around and started overlapping itself, and that works. It will overlap itself for odd numbers. It won't overlap with itself for even numbers. Okay, maybe. All right, and in the homework, you've got to graph some of them and create the table of values, and you'll see it happening as you do it. Okay. Does this have any symmetry? If you can't remember the right word, just use whatever you think of. It does have symmetry, doesn't it? Just look at it visually. Is it symmetric with respect to something? Somebody's got a really good question in private chat. Yes, you got to graph these by hand. You can check them all day long on a graphing calculator or a Desmos. You can check them. I want to see the tables being created. I want to see the points being plotted. Otherwise, what's the point, right? This is not learn how to push buttons class, right? But all day long, check your damn work. Of course, check your work, but start with the work, right? Do this by hand. Okay, I got somebody. Horizontal symmetry. Okay. So it's symmetric around the x-axis. Does somebody remember what that's called in polar coordinates? The x-axis. What's the x-axis called in polar coordinates? Does anyone remember what in polar coordinates what the x-axis is called?
The polar axis?
Holy shit! Yes.
I wanted to call it the Polar Express because that's what you keep calling it.
I know. Well, I did it once, but you're right. I did. Let me think. Okay. Is that all right, guys? I mean, again, you have to get into this and try it yourself. Until you do, you don't even know what to ask, right? Okay. Maybe. And part of this really is just play around with shit. Why not? What if you did sine of cosine of something? Did anyone think about trying that shit out? I don't know. Look at that shit. So what do you do when it's really tiny like that? That looks like a tiny little, what do you call it? Starfish. So what you do is you put a coefficient in front. Let me put 6 there. So that'll blow it up. That's interesting. Sine of cosine of 5 theta. That is interesting. That is freakadelic. Why is it doing that? That's freaking me out. I don't remember that. Oh, too bad, Jeff. You got a bad memory. Okay. Enough of that. So we're going to move on, unless there's any other specific questions. Okay, I think you guys should have enough to go on when you get into the section. You can always just make a big ass table of values, right? But it's not bad to look for symmetry. It's not bad to look for patterns, so you don't have to plug everything in. If it builds up to a maximum, it's probably going to build back down to the minimum, right? So you don't have to redo all the values. Okay, maybe. Okay, so we're going to do the next idea, and then we're going to call it a night because it's already 6:30. That's insane. And this next idea, let me go up to the board. I'm sitting on my ass too much nowadays. I know, hold on. So guess what's coming back? Guess what's coming back in a small way, a very small way, are complex numbers. We're not going to suddenly start graphing with complex numbers. Don't freak out. Do you guys remember the complex, how to plot a complex number? Where you have, this is the real axis. And this is the imaginary axis. Yes, no, maybe so. So if I want to plot the point, what do you got, Jeff? I don't know, hold on. 4 minus 3i, where would that be?
Would it be to the right 4, down
Yep.
3?
Because that's real. The real part's 4. I like it. And then down 3 because that's imaginary. So this is 1, 2, 3, 4. This is I, 2i. But you really just can do this better, Jeff. Negative I, negative 2i, negative 3i, negative 4i. So 4 minus 3i. 4 minus 3i would be right there. Now don't forget, this is reality. This is a little peek into what really happens. When you draw a number line, that's the real part of it. On the side is the imaginary part, and that is actually what it is. The word sucks. They aren't imaginary, right? That video we watched wanted to call them lateral, and I like that better because it just means on the side. I want some real numbers. You want some imaginary on the side? That was bad. That was even bad. I can't even accept that joke. Can somebody tell me how far that point is away from the origin? How long is this? So it's 4 units here and it's 3 units on the imaginary, right?
Is it 5?
Yeah. Right? Are you guys with me? So no. Here we go. Here's the new shit. Here comes the new stuff. We give the letter Z as the most basic complex number representation. So this complex number is, I can call it Z1 just to be like that. So the letter Z very often means complex number. All right, now Now this is really cool. All right, now stay with me. This is, come on. And again, I got one face to look at, so I don't even know if anybody's paying attention besides Amber. This is really flipping cool. This is so cool. You got to stay with me. Remind me real quick what an absolute value means. Like, why is the absolute value of 2 and -2 the same?
Because it's the distance away from the origin.
Kick ass. I love it. The distance, and that's exactly what it is, right? So this number we just figured out, isn't that how far that is from the origin? Isn't that how far that point is from the origin? Yes, right? Are you guys with me?
Yes.
So that is the absolute value. That's the absolute value of the complex number. What the shit? Because I really want us to put it all together. Absolute value is how far it is from the origin. So an imaginary number is going to be some diagonal away. So it's not going to be as easy as the absolute value of a real number, right? Of course, we wouldn't expect that. But you probably did, if I would have said, what's the absolute value of a complex number? You would have been like, how the shit would I know? Well, now it's freaking easy as shit. Right? Maybe? So what's the formula for a general, if I have a complex number, what's the formula for its absolute value? You got that easy because it was 3, 4, that's 5, but what's the general way you do that?
Is it the square root of a squared plus b squared?
Totally. All day long. I like it. Okay, so that's pretty simple, right? So that's the absolute value of the complex number. Can somebody figure out what this angle is here? Let me see. What is this angle here?
Isn't it equivalent to the angle across from side 3?
Totally. It's alternate interior angles. I don't know if you guys remember that. It's going to be the same as this. Because you actually can just copy this triangle here, right? So instead of doing that, you just copy the angle in there. Is everybody with that? And then it's just what? And then what's the angle? Well, let's see. For this one, so that's 5. So for this one, the angle would be what? The inverse who's a what of which what? Do it related to the things we know. It would be the inverse what?
Inverse tangent of
Tangent.
3/4.
Doesn't this feel a lot like what we're doing with changing polar coordinates to rectangular and vice versa? Remember that? This is exactly what it is, because all complex number plane is, it's very much like the XY plane, of course. So in general, what's theta going to be? It's going to be the inverse tangent of y over x, right? And the y is the imaginary, so b over a. Okay, maybe. All right, now. Let me see if I can bring this together. So those, let me see. These are the important things. Let me keep this here. This is the general way to do this piece. All right, and then we still have to put this together into its final form, like golden freezer or something. So if I have, let me give you a different, let me do this in a different color. Let me give you one that works out nice. See what that feels like. Yeah, we can do, sure, I like it. But believe it or not, it's going to work out nice. Figure out what the absolute value is and figure out what the angle is. And you should be able to get the exact answer for the angle.
Is it 2?
Is what 2? Sorry.
Is the absolute value of z 2?
Yeah, because in this case, A is what and B is what? A is real and B is imaginary. So A is rad 3 and B is -1. Right? So then you get the square root of rad 3 squared is 3, -1 squared is 1. Kick ass. And then this is going to be the inverse tangent of B over A, right? B over A. Y piece over the X piece. And that should be one you know, maybe. No. So it's going to be the smaller, tangents like sine. So this is the smaller thing it could be, rad 3 divided by 3. The bigger option is rad 3. So since it goes like sine, when is sine smaller? Which angle is sine smallest at without being 0?
Pi over 6 or 30 degrees.
Yes. And it's negative, so it'll be negative pi over 6. And let's double check. Where is this? What quadrant is that in? So since it's inverse trig, this could be just a reference angle, but what quadrant will this be in? Well, it goes rad 3 and it goes down, so it is in quadrant 4. You with me? So that is a valid negative pi over 6. That looks like where it should be. All right. So now let's kind of put this all together. Boom, 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 ba-doom. So here's the freaky way we do this. And at first it's going to seem like there's no point to this, and I understand that. But then almost immediately there's going to be a beautiful thing that happens. So you just have to trust me in that. Let me see if you guys are cool with this. So if I say that, let's just cut to the chase and say what this really is. Do you understand what I mean when I write this? It kind of makes sense because that's the x-axis, the real axis, and the y-axis is like the imaginary. So if I have, and let me do something else too. Instead of just always doing absolute value of z, we just call this r, which kind of makes sense because it is the distance I go out away from the origin. All right, now you're ready. So if I have a complex point, it doesn't really matter where it's at. And it's got r and it's got theta. Then what would the x be and what would the y be? Well, the x would be r cosine theta and the y would be r sine theta. So this is the full way to represent a complex number in polar form. How do I figure out what theta is? Inverse tangent of b over a. How do I figure out what r is? Find the absolute value. Do the distance formula, right? Maybe. Okay, let me see how much time do I have. Not much. This is going to be one night when we go a little bit longer, so too damn bad. Here we go. Let me see if I can push this a little bit. So if I have, let's see, I have one complex number here. So I'm going to call it R1 cosine theta 1 plus I R2. Let me just do this. It's not 2, Jeff. There. Plus I sine theta 1. And I got Z2 is R2 cosine theta 2 plus I sine theta 2. Okay. All right, that's plenty, right? Do you want more? No. So those are two different complex numbers. What do I get Oh, you're gonna love this shit. You're gonna love this. What do I get when I multiply them together? This is the last thing we'll do, I promise. Next time we'll pick it up with what do we get when we divide them? Okay. So if I multiply this by this, let me just get these out of the way. That's R1 times R2. And then this should have got to FOIL out. Is that cool? So I get cosine theta 1, cosine theta 2. Hopefully I got enough room with this tiny little whiteboard. Dadgummit. Plus I sine theta 2, cosine theta 1. I'm not going to have enough room. It's fine, Jeff. Plus I sine theta 1, cosine theta 2. Is everybody? I'm just freaking foiling things out, right? That's all I'm doing. And you're not having enough faith right now. This is going to come out nice. And then what happens when I multiply these two? What's I times I?
-1.
Good. So minus sine theta 1, sine theta 2. Ah, scheisse. Scheisse. All right. All right, now watch. All the stuff without eyes. Right? All the stuff without eyes. Does this look familiar at all to anybody?
Isn't that cosine 2 theta or cosine theta of 1 plus theta 2?
Yes, plus cosine, that's a minus. So cosine, me first, it must be cosine. And it's a minus, so it's going to be a plus of these angles. So that's the real part. I don't know what the hell I did to you. And then what's the I shit? Let me take an I out. Ow, shit. Took my I out. And then what happens here? This, of course, is going to be sine, cosine. It's going to be sine, right? That's the nice guy. Everybody takes a turn. Sine of theta 1 plus theta 2. I have no idea why I put an extra thing in there. I need you back here. Bam. This is kind of nifty that if I represent complex numbers in this way, I can just multiply their lengths and then add their angles. So if I had to do, so this leads to, the next thing we'll do next time is, what if I raise a complex number, I multiply it by itself multiple times? It's going to be easy as shit using this idea. So if I told you what's 4 plus 3i to the 87th power, you would be rightfully looking at me like, I ain't doing it. But now, with what we're going to do next, that is going to be relatively easy. Okay, maybe. That's plenty. So let me know if you need to stay after and ask questions. Otherwise, you are free to go.
I had a quick question, actually.
Yes.
Do you have a teacher that you recommend for Math 180?
Oh, let's see. Who's teaching? That's a good point, because you guys, when is your registration date?
I think it's the end of November.
So maybe, yeah, I always like to discuss.
Mine's on the 18th.
Let me make this